So here's something to sit with for a moment. Right now, wherever you are, gravity is pulling on you. You can feel it. It's pressing you into your mattress, or your pillow, or whatever you're resting against. It's the most familiar force in your life. You've never known a single second without it. And yet, if you follow that force, if you really chase it down to its most extreme, most absurd, most beautiful conclusion, you end up at a black hole. You end up at a place where gravity gets so intense that it swallows light itself, where time slows down and eventually, in a sense, stops, where the rules you've lived with your entire life just quietly break apart. And the wild thing is, we figured this out. Humans, sitting on a small rocky planet, worked out that these things must exist. Mathematically, theoretically, more than a century before we ever actually saw one. That's the story I want to tell you tonight. Not just what black holes are, although we'll get deep into that, but how we came to understand them. The people, the arguments, the wrong turns, the moments of genuine shock when the math said something so strange that brilliant physicists simply refused to believe it. Because that's what happened, again and again. The universe kept telling us something extraordinary, and we kept saying no. That can't be right. Let's start where it actually starts, which is much further back than most people realize. The year is 1783. The American Revolution just ended. Mozart is alive and composing in Vienna. And in England, a quiet, largely forgotten clergyman and natural philosopher named John Michell is sitting down to write a paper for the Royal Society. Michell is one of those figures history has been unfairly unkind to. He was genuinely brilliant. He invented the torsion balance, which Henry Cavendish later used to weigh the Earth. He did foundational work on earthquakes after the Great Lisbon earthquake of 1755. He was the first person to suggest that double stars might be physically orbiting each other rather than just appearing close together in the sky by coincidence. The man had range. But the idea he's about to put on paper is the one that should have made him immortal, and almost nobody knows about it. Michell understood Newton's theory of gravity. Everything pulls on everything else, and the more massive something is, the harder it pulls. He also understood that light travels at a finite speed, and he asked himself a beautifully simple question. What if a star were so massive and so dense that its gravitational pull was strong enough to prevent light from escaping? Think about what he's really asking. You throw a ball into the air, and gravity pulls it back down. You throw it harder, it goes higher before coming back. There's a speed, we call it escape velocity, where if you throw the ball fast enough, it never comes back. It escapes the gravitational pull entirely. For Earth, that escape velocity is about 11 kilometers per second, roughly 25,000 miles per hour. For the Sun, it's much higher, around 617 kilometers per second. Michell just followed the logic. If you had a star massive enough, the escape velocity at its surface could exceed the speed of light, and if light can't escape, you can't see it. The star would be dark, invisible. It would still be there, still pulling on things around it with its gravity, but no light would ever leave it. He calculated that a star with the same density as the Sun, but about 500 times its diameter, would have an escape velocity greater than the speed of light. He called these objects dark stars, and then he published the paper. It was read before the Royal Society in 1783, and basically, nothing happened. People noted it. The great Pierre-Simon Laplace independently came up with the same idea about a decade later, in 1796, and included it in his book on celestial mechanics, but then Laplace quietly removed it from later editions. The idea just sort of faded away. And here's why that matters. Michel and Laplace were working with Newton's physics, with the idea that light is made of tiny particles that gravity pulls on, just like it pulls on cannonballs. When the wave theory of light took over in the early 1800s, the whole concept stopped making sense. If light is a wave, why would gravity affect it? Waves aren't objects. You can't grab a wave and pull it back down. So the dark star idea seemed like a dead end, a curiosity from an older way of thinking. And for over 100 years, that's exactly what it was. But the universe is patient. It doesn't care whether we're ready for its truths or not. And the next chapter of this story begins with someone you've definitely heard of, Albert Einstein, and a year you should remember, 1915. Now I want to be careful here, because the story of Einstein and general relativity is often told in a way that makes it sound like a single flash of genius, like he just sat down one afternoon and rewrote physics. The reality is so much more human than that. Einstein struggled with this theory for nearly a decade. He started working on it around 1907, and there were years where he was lost. He'd go down mathematical paths that turned out to be dead ends. He'd publish results that he later had to retract. He was trying to do something that no one had ever done before. Describe gravity, not as a force that pulls objects toward each other, the way Newton described it, but as something fundamentally different, something geometric. Here's the idea, and it's worth spending some time with because everything about black holes flows from this. Imagine you have a large, flat rubber sheet stretched tight, like a trampoline. Now you place a bowling ball in the center. The sheet sags, right? It curves around the bowling ball. Now, if you roll a marble across the sheet, it doesn't travel in a straight line anymore. It curves toward the bowling ball. Not because the bowling ball is reaching out and pulling the marble. There's no invisible rope between them. But because the marble is following the curved surface of the sheet. It's taking the most natural path it can through a curved space. That's the core insight of general relativity. Mass and energy curve space-time, not just space, but time too, and we'll come back to the time part, because it's crucial for black holes. Objects then move through that curved space-time along the most natural paths available to them. What we experience as gravity, that force pressing you into your bed right now, isn't really a force at all. It's geometry. The Earth's mass is curving the space-time around it, and you're following that curvature. You feel it as weight. You feel it as down. But it's the shape of space-time itself. Now, that rubber sheet analogy is useful, but it's also a little misleading, and I want to be honest about that. The actual mathematics of general relativity are described by what are called the Einstein field equations, and they are notoriously, almost comically difficult. They relate the curvature of space-time on one side of the equation to the distribution of mass and energy on the other side. Solving them exactly for any given situation is incredibly hard. Einstein himself didn't think exact solutions would come easily. He expected people would spend years developing approximate methods, slowly chipping away at special cases, which is what makes what happened next so surprising. Einstein published his final field equations in November 1915. And just weeks later, a German physicist and astronomer named Karl Schwarzschild found the first exact solution. And he did it while serving on the Eastern Front of World War I. Let that sink in for a moment. Karl Schwarzschild was not sitting in a comfortable university office. He was a 41-year-old scientist who had volunteered for military service He was calculating artillery trajectories for the German army in Russia. He was already suffering from a painful autoimmune skin disease called pemphigus, which would kill him within months. And in between the shells and the cold and the illness, he got hold of Einstein's papers, and he solved the equations for the simplest possible case: the space-time around a perfectly spherical, non-rotating mass. He sent his solution to Einstein in a letter in December 1915. Einstein was reportedly stunned, both by the elegance of the solution and by the speed with which Schwarzschild had found it. He presented Schwarzschild's paper to the Prussian Academy of Sciences in January 1916. Schwarzschild himself died on May 11, 1916, at the age of 42. He never saw the full implications of what he'd found. And here's where things start to get strange. Schwarzschild's solution described the curvature of space-time around a spherical mass beautifully. It matched Newtonian gravity in the weak field limit. Meaning, for everyday situations, like planets orbiting the sun, it gave you basically the same answers Newton would, just slightly more precise. It predicted the bending of light around massive objects, the slight shift in Mercury's orbit that Newton couldn't explain, all the things that would later be confirmed and make Einstein famous. But the solution also contained something deeply unsettling. There was a special radius, a distance from the center of the mass, where the math did something bizarre. At this radius, one of the terms in the equation went to infinity. The math blew up, and if you looked at what happened inside that radius, the roles of space and time appeared to switch. Time became space-like, space became time-like. It was as if, once you crossed that boundary, moving forward in time was the same as moving inward toward the center. You couldn't stop yourself from falling inward any more than you can stop yourself from moving forward in time right now. That special radius is what we now call the Schwarzschild radius, or the event horizon. For an object with the mass of our sun, it's about 3 kilometers, just under 2 miles. For the Earth, it would be about 9 millimeters, roughly the size of a marble. The idea is that if you could somehow compress all the mass of the sun into a sphere just 3 kilometers across, space-time would curve so severely at that surface that nothing, not light, not anything, could escape from inside it. But here's the thing. Almost nobody in 1916 took this seriously as a physical possibility, including Einstein. They saw that singular point in the math, that place where the equation blew up, and they assumed it meant the solution was breaking down, that it was a mathematical artifact, not a real physical prediction. And honestly, that's a reasonable reaction. When your equation gives you infinity, it usually means you've pushed it past the point where it applies. It's like dividing by 0. The math is telling you something has gone wrong, not that infinity literally exists somewhere. Schwarzschild himself seems to have viewed it primarily as a mathematical curiosity. The prevailing attitude for years, decades even, was that no real object in nature could ever actually be compressed to its Schwarzschild radius. Stars are big, fluffy things. The sun is nearly 1.5 million kilometers across. The idea that it could be squeezed into a ball 3 kilometers wide seemed absurd. There had to be some physical mechanism, some pressure or force that would prevent matter from ever collapsing that far. And for a while, that seemed like a perfectly safe assumption. The physics of stellar structure, which was being worked out in the 1920s and 1930s, showed that stars are held up by the pressure of their own radiation and the thermal energy of their gas. A star is essentially a controlled thermonuclear explosion, and the outward pressure of that explosion balances the inward pull of gravity. It's a tug of war, and for most of a star's life, the two sides are evenly matched. But stars don't burn forever. They run out of fuel, and when they do, that outward pressure starts to fade, and gravity begins to win. So the question becomes, what happens when a star dies? What stops it from collapsing? Is there always something that catches it, some floor it hits? Or could a star, under the right circumstances, just keep falling inward, past every possible defense, all the way down to its Schwarzschild radius and beyond? That question, that deceptively simple question, would ignite one of the most bitter and fascinating scientific arguments of the 20th century. And at the center of it, on opposite sides, would stand two extraordinary physicists, a young Indian prodigy named Subramanian Chandrasekhar, barely out of his teens, and the most famous astrophysicist in the world, a towering figure named Arthur Stanley Eddington. What happened between them is one of those stories that changes the course of science and breaks a man's spirit at the same time. Subramanian Chandrasekhar, Chandra as almost everyone called him, was born in 1910 in Lahore, which was then part of British India. He came from a family that valued learning almost above everything else. His uncle, C.V. Raman, would go on to win the Nobel Prize in Physics in 1930 for his work on light scattering. So brilliance ran in the family, and Chandra showed it early. He was the kind of student who didn't just do well. He consumed material, devoured textbooks, pushed beyond what his professors were teaching. By the time he was 18, he had already published his first scientific paper. And in 1930, at the age of 19, he boarded a ship from Bombay to England, headed for Cambridge to begin his graduate studies under the great Ralph Fowler. Now, here's where the story gets extraordinary, because it was on that ship, during the long, slow voyage from India to England, that Chandra did the work that would define his life. He had time, weeks of open ocean, nothing to do but think. And what he was thinking about was exactly the question we just arrived at. What happens when a star runs out of fuel? By 1930, physicists had already figured out part of the answer. A few years earlier, Ralph Fowler himself had shown that when an ordinary star like the Sun exhausts its nuclear fuel and can no longer sustain the outward push of radiation pressure, it doesn't just collapse into nothing. Instead, it shrinks down into a very dense, very compact object, what we call a white dwarf. And white dwarfs are held up by something different from the radiation pressure that supports a living star. They're held up by a quantum mechanical effect called electron degeneracy pressure. Let me explain that, because it's actually beautiful. You've probably heard of the Pauli exclusion principle, the rule in quantum mechanics that says no two electrons can occupy the exact same quantum state. It's one of the deepest rules in physics, and it has this remarkable consequence. If you try to squeeze electrons into a smaller and smaller space, they resist, not because of any force between them in the usual sense, but because the laws of quantum mechanics literally forbid them from all being in the same state. The closer you pack them, the faster some of them have to move, and that motion creates a pressure, degeneracy pressure. It's not thermal. It doesn't depend on temperature. It's purely a consequence of quantum mechanics and the fact that electrons are fermions, particles that obey the exclusion principle. So Fowler's picture was reassuring. A star dies, it contracts, the electrons get squeezed together, degeneracy pressure kicks in, and the star settles into a stable white dwarf. Gravity is balanced. Collapse is halted. Everything is fine. There's a floor. The star hits it and stops. But Chandra, sitting on that ship in the middle of the Indian Ocean, realized something that Fowler had missed. Fowler had done his calculation using ordinary, non-relativistic quantum mechanics. He'd treated the electrons as if they could move at any speed necessary to provide enough pressure. But Chandra knew, because he'd been reading the latest work by people like Sommerfeld and Dirac, that when electrons are squeezed hard enough, they start moving at speeds approaching the speed of light. And when that happens, you can't ignore special relativity anymore. The relationship between their speed and their energy changes. The pressure they can exert doesn't grow as fast as you'd expect. Relativity puts a kind of speed limit on the electrons, and that speed limit puts a ceiling on the degeneracy pressure they can provide. Think about what that means. If there's a ceiling on the pressure, then there might be a star massive enough that its gravity exceeds that ceiling. And if it does, the degeneracy pressure can't hold it up. There is no floor. The star just keeps falling. Chandra worked through the mathematics during the voyage, and what he found was startling. There was a specific mass, a limit, above which a white dwarf could not exist. If the remnant core of a dead star was heavier than about 1.4 times the mass of the Sun, electron degeneracy pressure would not be strong enough to support it. The star would have to keep collapsing. He couldn't say exactly what it would collapse into. That was a question for another day. But the implication was clear and unsettling. Nature did not guarantee a safe stopping point. For big enough stars, the collapse could go all the way. That number, 1.4 solar masses, is what we now call the Chandrasekhar limit, and it's one of the most important numbers in all of astrophysics. It tells you the dividing line between stars that die quietly as white dwarfs and stars that face something far more dramatic. And Chandra figured it out at 19, on a boat, with a pencil. He arrived at Cambridge, refined his calculations over the next few years, and by January 1935, he was ready to present his results to the Royal Astronomical Society in London. He was 24 years old. He had every reason to believe this would be a triumph. The math was solid. The physics was clear. He'd been careful, methodical, thorough. And then Arthur Stanley Eddington stood up. You need to understand who Eddington was to appreciate the full weight of what happened next. Eddington was not just any physicist. He was arguably the most famous astrophysicist alive. He was the man who in 1919 had led the solar eclipse expedition that confirmed Einstein's general relativity, the bending of starlight around the sun. That single experiment had made Einstein a global celebrity, and it had made Eddington the most respected astronomer in the English-speaking world. He was brilliant, eloquent, commanding. When Eddington spoke, people listened. When Eddington rendered a judgment, careers were made or destroyed. Eddington had actually been friendly with Chandra. He'd encouraged the young man's work. He'd seen early versions of the calculations, so Chandra had no reason to expect what was coming. After Chandra presented his results to the Royal Astronomical Society, Eddington rose to give the next talk, and he used it to demolish Chandra's work. Not on mathematical grounds. Eddington didn't find an error in the equations. Instead, he attacked the conclusion on what you might call aesthetic or philosophical grounds. He declared that the idea of a star collapsing without limit was absurd. He called it a reductio ad absurdum, a result so ridiculous that it proved the theory must be wrong somewhere. He said there ought to be a law of nature preventing such a thing, and he proposed his own alternative theory, one that conveniently avoided the problem. Here's the thing. Eddington was wrong. His alternative theory didn't hold up, and Chandra's mathematics was correct. Other physicists, including some of the best in the world, knew Chandra was right. But Eddington's authority was so immense, his reputation so towering, that most of the scientific community simply deferred to him. Nobody wanted to publicly contradict the great Eddington. The few who did, like the brilliant Polish physicist Leon Rosenfeld, were largely ignored. The effect on Chandra was devastating. He didn't abandon the result. He knew he was right. But he essentially abandoned the field. He moved on to other areas of astrophysics, other problems, rather than spend his career fighting a battle against Eddington's prestige. He later described the experience as deeply painful. Decades later, when he finally received the Nobel Prize in 1983 for this very work, among other contributions, there was a bittersweet quality to it. The recognition had come, but it had come nearly 50 years late. And the tragedy extends beyond Chandra personally, because Eddington's opposition didn't just hurt one man's career. It slowed down the entire field. If the scientific community had accepted the Chandrasekhar limit in 1935 and followed its implications, the theoretical study of gravitational collapse might have advanced a generation earlier. The questions that Chandra's work raised: what happens to a star heavier than 1.4 solar masses? What does it become? Those questions hung in the air, mostly unanswered for decades, but not entirely unanswered, because even while Eddington was dismissing the possibility of total collapse, other physicists were quietly poking at the problem from different angles, and one of them would take the next crucial step, arriving at a result so strange that even he seemed uncomfortable with it. His name was J. Robert Oppenheimer. Yes, that Oppenheimer, the same man who would later lead the Manhattan Project and become the most famous scientist of the atomic age. But in 1939, 6 years before Hiroshima, Oppenheimer was a theoretical physicist at Berkeley, and he was interested in what happens to stars that are too massive to become white dwarfs. By this point, there was actually an intermediate possibility on the table. In 1934, just a year before the Eddington-Chandra confrontation, two astronomers named Walter Baade and Fritz Zwicky had proposed that when massive stars explode as supernovae, they might leave behind an incredibly dense remnant made not of ordinary atoms, but of neutrons. A neutron star. The idea was that under extreme pressure, the electrons and protons in the star's core would be squeezed together to form neutrons, and then neutron degeneracy pressure, the same kind of quantum mechanical resistance, but now from neutrons instead of electrons, would hold the star up. A neutron star would be fantastically dense. A teaspoon of neutron star material would weigh about 1 billion tons, but it would be stable. It would be another floor, another stopping point. So maybe that was the answer. Maybe stars too heavy for white dwarf status simply became neutron stars, and that was the end of the story. Gravity gets caught again, just at a deeper level. Oppenheimer wasn't so sure. Working with his student George Volkoff, he calculated the structure of neutron stars in 1939 and found that they too had a mass limit. Just like Chandra's limit for white dwarfs, there was a maximum mass that neutron degeneracy pressure could support. The exact number was harder to pin down because the physics of nuclear matter at those densities was poorly understood, but it was somewhere in the range of 2 to 3 solar masses. Above that, even neutrons couldn't hold the star up. And then, in a remarkable paper published in September 1939, the very same month that Germany invaded Poland and the world plunged into war, Oppenheimer and another student, Hartland Snyder, asked the obvious next question. They asked what happens to a star that exceeds even the neutron star limit. What happens when there is no floor left? And they worked it out, using Einstein's general relativity. And what they found was extraordinary and deeply unsettling. What they found was that the star just keeps collapsing. There's no bounce. There's no new floor. There's no previously unknown force that steps in at the last moment to save the day. Once a star exceeds the maximum mass that neutron degeneracy pressure can support, gravity wins completely and absolutely, and the matter falls inward without limit, crushing itself smaller and smaller, denser and denser, until it reaches a point of infinite density, a singularity. The very thing Schwarzschild's math had predicted back in 1916, that troubling point at the center of his solution where the equations blow up to infinity. Oppenheimer and Snyder were now saying it actually happens. It's not a mathematical artifact. It's not a quirk of the coordinates. It's a real physical outcome. A massive enough star, at the end of its life, will collapse through every possible barrier and form exactly the kind of object that everyone had been dismissing as impossible for over 2 decades. And here's what makes their paper even more remarkable. They didn't just say the star collapses to a singularity. They described what the collapse would look like from the outside. They showed that as the star's surface falls inward and approaches the Schwarzschild radius, that critical boundary we talked about earlier, something very strange happens to the light it emits. The light gets increasingly redshifted. You remember how gravity stretches light, pulling it toward longer, redder wavelengths? Well, as the surface of the collapsing star approaches the Schwarzschild radius, that redshift becomes more and more extreme. The light gets dimmer and dimmer. The wavelengths stretch longer and longer. And from the perspective of a distant observer, someone watching from a safe distance, the star appears to slow down as it approaches that boundary. It never quite seems to cross it. It just fades, getting redder and dimmer and slower, asymptotically approaching the Schwarzschild radius, but never quite reaching it. The star doesn't disappear with a bang. It disappears with a whisper. It redshifts itself into invisibility. Now think about what that means. From the outside, you'd see this dying star gradually wink out of existence. The last photons it emits would be stretched to such enormous wavelengths that no telescope could ever detect them. The star would effectively vanish from the observable universe, leaving behind only its gravitational influence, a region of space-time so severely warped that nothing, not even light, could escape from it. But, and this is the part that really bends your mind, from the perspective of someone riding on the surface of the collapsing star, the experience would be completely different. For that unfortunate observer, the collapse happens quickly. They'd cross the Schwarzschild radius without even noticing anything special about that particular moment. There's no wall there, no barrier, no sign that says point of no return. They'd just sail right through. It's only afterward, when they tried to send a signal back outward, that they'd realize something had fundamentally changed. The signal would never make it out. They're inside the event horizon now, and every direction they can move, even outward, leads deeper into the collapsing star. The geometry of space-time itself has been rearranged so that the singularity isn't a place in space anymore. It's a moment in time. It's in their future, and they can no more avoid it than you or I can avoid next Tuesday. That asymmetry, the radical difference between what an outside observer sees and what a falling observer experiences, is one of the most profound and counterintuitive consequences of general relativity. And Oppenheimer and Snyder laid it all out in 1939. They had, for the first time, described the complete formation of what we would eventually call a black hole. They showed the mechanism. They showed the observable signatures. They showed that Einstein's own theory, taken seriously and followed to its logical conclusion, predicts objects so extreme that they essentially remove themselves from the universe while still shaping the space-time around them. And the world barely noticed. The paper was published on September 1st, 1939. Literally the same day German tanks rolled into Poland. Within weeks, the scientific community's attention was consumed by far more immediate concerns. And Oppenheimer himself, well, you probably know what happened to Oppenheimer. Within a few years, he was leading the Manhattan Project at Los Alamos, directing the effort to build the atomic bomb. The man who had just demonstrated that stars can collapse into objects of infinite density was now focused on a very different kind of physics, the kind that splits atoms apart rather than crushing them together. He never returned to the problem of gravitational collapse in any serious way. The paper sat there in the Physical Review, technically available for anyone to read, but effectively forgotten. The physics community moved on. The war consumed everything. And honestly, even without the war, it's not clear the paper would have gotten the attention it deserved. The prevailing attitude among physicists was still deeply skeptical. Most people who thought about it at all assumed that some unknown physical mechanism would prevent complete collapse. Maybe at high enough densities, nuclear forces would behave differently than expected. Maybe general relativity itself broke down under such extreme conditions and needed to be replaced by a better theory. The idea that nature would actually allow a singularity to form, a point of genuinely infinite density, struck most physicists as absurd. It felt like the theory was telling you something had gone wrong with the theory, not that something extraordinary was happening in the real universe. This attitude persisted for nearly 20 years. Through the 1940s and most of the 1950s, gravitational collapse was a backwater of physics. Almost nobody worked on it. The few people who did were largely ignored. General relativity itself was considered a beautiful but somewhat impractical theory. Elegant mathematics with limited relevance to the real world of particle physics and quantum mechanics, which is where all the excitement and funding were. There's a famous quip from that era that general relativity was a subject with a great deal of matter, but very little substance, meaning the theory dealt with massive objects, but had very few practitioners and very few testable predictions. But here's the thing about physics. You can ignore an inconvenient prediction for a while, but if the math is right, reality has a way of eventually forcing the issue. And the issue got forced in the most spectacular way possible, starting in the late 1950s and accelerating through the 1960s in what's sometimes called the golden age of general relativity. Several things happened almost simultaneously to revive interest in gravitational collapse. First, there were new astronomical observations that didn't fit neatly into existing theories. Radio astronomers were discovering incredibly powerful sources of radio waves in the sky, objects that seemed to be pouring out more energy than entire galaxies, yet appeared almost point-like, like stars. These were eventually called quasars, short for quasi-stellar radio sources, and when their distances were measured in the early 1960s, the energy requirements turned out to be staggering. What could possibly power something that luminous? the answer that gradually emerged was gravitational energy, matter falling into an extremely deep gravitational well, converting its energy into radiation with extraordinary efficiency. And the deepest gravitational well imaginable was exactly the kind of collapsed object Oppenheimer and Snyder had described. Second, there was a new generation of theorists who were willing to take general relativity seriously as a physical theory, not just a mathematical curiosity. People like John Wheeler at Princeton, who had actually been one of the skeptics. He'd spent years trying to find a way to avoid the conclusion of complete collapse, looking for some physical mechanism that would prevent singularity formation. But by the late 1950s, Wheeler had come around. He'd convinced himself that Oppenheimer and Snyder were right, that complete collapse was a genuine prediction of general relativity, and that the physics community needed to grapple with it seriously. Wheeler was a brilliant physicist and an even more brilliant communicator, and his enthusiasm was infectious. He started training a new generation of students to work on these problems, and it was Wheeler, incidentally, who gave black holes their name. Before him, these objects had been called frozen stars, or collapsed stars, or gravitationally totally collapsed objects, which, you have to admit, doesn't exactly roll off the tongue. At a conference in 1967, Wheeler started using the term black hole, and it stuck immediately. It was perfect. Two simple words that captured the essential nature of the thing. Black, because no light escapes. Hole, because anything that falls in doesn't come back out. But the real theoretical breakthrough of this era came from a quiet, meticulous mathematician named Roger Penrose. And what Penrose did in 1965 changed the entire conversation about gravitational collapse in a way that's hard to overstate. See, one of the lingering objections to the Oppenheimer-Snyder result was that their calculation assumed perfect spherical symmetry. Their collapsing star was an idealized, perfectly round ball of matter, collapsing uniformly inward from all directions. And critics argued, reasonably enough, that real stars aren't perfectly spherical. Real collapse would be messy and asymmetric. Maybe in a realistic collapse, the infalling matter would miss the center, swirl around, bounce off itself, and somehow avoid forming a singularity. Maybe the singularity was an artifact of the unrealistic symmetry assumption. Penrose demolished this objection. Using a set of elegant mathematical tools, new techniques involving what he called trapped surfaces, he proved a theorem showing that once a collapsing object passes a certain point, singularity formation is inevitable regardless of symmetry. It doesn't matter if the collapse is lumpy, asymmetric, chaotic, or messy. Once enough mass is concentrated in a small enough region, the geometry of space-time guarantees that a singularity will form. There's no escape clause, no loophole. The theorem is remarkably general. It doesn't depend on the specific properties of the matter, or the equation of state, or the details of the collapse. It just depends on a few very basic assumptions about the nature of space-time and gravity, assumptions that essentially any reasonable physical theory would satisfy. This was a thunderbolt. Before Penrose, you could still hope that singularities were a special case, an artifact of oversimplified models. After Penrose, you had to accept that they were a generic prediction of general relativity. If the theory was right, and every test of general relativity had confirmed it, then singularities were real, and black holes were real, and the universe contained objects where the known laws of physics simply break down. Penrose's singularity theorem earned him the Nobel Prize in Physics, though not until 2020, more than half a century after the work was done. He shared it with Andrea Ghez and Reinhard Genzel, who had provided the most compelling observational evidence for a supermassive black hole at the center of our own galaxy. but we'll get to that. For now, what matters is that by the mid-1960s, the theoretical case for black holes had gone from probably nonsense to almost certainly real, and the observational evidence was beginning to pile up in ways that couldn't be ignored. And this is where the story takes another fascinating turn, because once physicists accepted that black holes were real, they started asking a new set of questions. Not just, can they form? But what are they like? What are the properties of a black hole? If you could somehow observe one, what would you see? And it turns out that black holes, despite being the most extreme objects in the universe, are also in some sense the simplest. A black hole has no hair. That's actually the technical phrase physicists use, the no-hair theorem, and it means that a black hole can be completely described by just three numbers: its mass, its electric charge, and its spin. That's it. It doesn't matter what the star was made of before it collapsed. It doesn't matter whether it was composed of hydrogen or iron or hypothetical strange matter. It doesn't matter what shape it was, or what its temperature was, or what its chemical composition was. Once it collapses into a black hole, all of that information is lost. The black hole remembers only three things about its past: mass, charge, and spin. And honestly, when you sit with that idea for a moment, it's one of the strangest things in all of physics. Think about what it means. A star, a real star, with a history, with layers of different elements forged over millions of years, with magnetic fields and sunspots and convection currents and maybe even planets orbiting it. All of that complexity, all of that identity, gets swallowed up and reduced to three numbers. It's like taking an entire library, every book, every page, every word, and compressing it into a single card that says only how much the library weighs, whether it's electrically charged, and whether it's spinning. Everything else is gone, erased, not hidden somewhere inside, actually gone, as far as the outside universe is concerned. Now, in practice, the electric charge part almost doesn't matter. And here's why. If a black hole somehow formed with a significant electric charge, it would immediately start attracting oppositely charged particles from the surrounding space, electrons, ions, whatever's floating around, and those particles would fall in and neutralize the charge almost instantly on astronomical timescales. So real astrophysical black holes are expected to have essentially zero net charge, which means you're really down to just two numbers, mass and spin. That's what defines a black hole in the real universe. Two numbers. And from those two numbers, you can derive everything else about the black hole's geometry, its gravitational influence, the shape of space-time around it. Everything. Let's talk about mass first, because it's the more intuitive of the two. A black hole's mass determines its size, specifically the radius of its event horizon, and the relationship is beautifully simple. It's linear. Double the mass, double the radius. A black hole with the mass of our sun would have an event horizon with a radius of about 3 kilometers. That's roughly the size of a small town. The entire mass of the sun, compressed into a sphere you could almost drive across in a few minutes. A black hole with 10 solar masses would have an event horizon about 30 kilometers across. And the supermassive black holes at the centers of galaxies, the ones with millions or billions of solar masses, their event horizons can be enormous. The one at the center of our Milky Way, called Sagittarius, a star, has about 4 million solar masses, and its event horizon is roughly 12 million kilometers in radius. That sounds huge, and it is, It's about 17 times the radius of the Sun. But compared to the galaxy it sits in, it's a pinpoint, an almost incomprehensibly dense pinpoint. And here's something that might surprise you. The bigger a black hole is, the less dense it is. On average, anyway. Wait, that sounds wrong, doesn't it? How can the most massive black holes be less dense? But think about it this way. Volume scales with the cube of the radius, while mass scales linearly with radius for a black hole. So as you make a black hole more massive, its volume grows much faster than its mass does. A black hole with the mass of 4 million suns has an average density. If you just took the mass and spread it over the volume inside the event horizon, that's actually comparable to the density of water. And the truly enormous ones, the ultra-massive black holes with 10 billion solar masses or more, their average density inside the event horizon is less than the density of air. You could, in principle, be inside the event horizon of a sufficiently large black hole and not even notice anything unusual about the local conditions. No crushing forces, no obvious sign that anything has gone wrong. Except, of course, that you could never leave. Now, spin. This is where things get really interesting, and it's where a physicist named Roy Kerr enters the story. Remember, Schwarzschild's original 1916 solution described a black hole that wasn't spinning, a perfectly static, spherically symmetric object. And that was a beautiful mathematical result, but it had a problem. Real stars spin. Everything in the universe spins. And when a star collapses, conservation of angular momentum means it spins faster, the same way an ice skater spins faster when they pull their arms in. So any realistic black hole formed from a collapsing star should be spinning, potentially very fast. And for decades, nobody could solve Einstein's equations for a spinning black hole. It was one of the great unsolved problems in general relativity. Then in 1963, Roy Kerr, a New Zealand mathematician working at the University of Texas, found the solution. And it's worth pausing on this for a moment because the Kerr solution is one of the most important exact solutions in all of general relativity, and it came from a somewhat unexpected direction. Kerr wasn't a household name. He wasn't at one of the traditional powerhouse institutions for general relativity. He was a quietly brilliant mathematician who'd been working on a particular class of algebraic approaches to Einstein's equations, and he found something extraordinary. The Kerr metric, as it's called, describes the geometry of space-time around a spinning black hole, and it's dramatically different from the Schwarzschild solution. A spinning black hole isn't spherically symmetric anymore. It's oblate, slightly flattened at the poles, bulging at the equator, just like the Earth is, just like any spinning object is. But the really wild part is what happens to space-time itself near a spinning black hole. The spin doesn't just change the shape of the event horizon, it drags space-time along with it. Literally drags it. This effect is called frame dragging, or sometimes the lens-thirring effect, and it means that space itself is being twisted and pulled in the direction of the black hole's rotation. Think about it like this. Imagine you had a bowling ball sitting on a rubber sheet. That's the classic analogy for how mass warps space-time. Now imagine the bowling ball is spinning, and as it spins, it grabs the rubber sheet and twists it, so the sheet itself is being pulled around in a spiral. That's frame dragging. Near a spinning black hole, even if you fired your rocket engines at full blast trying to stay perfectly still, you couldn't do it. Space itself is moving, and you're being carried along with it, like a swimmer caught in a current. The closer you get to the black hole, the stronger this effect becomes, until you reach a boundary called the ergosphere. And inside the ergosphere, it's impossible to remain stationary relative to distant stars. You are forced to co-rotate with the black hole, no matter how powerful your engines are. Space is moving faster than light in a sense, dragging everything with it. And here's what's really clever about the ergosphere. It's not the event horizon. It's outside the event horizon. There's a region of space between the ergosphere and the event horizon where you're being dragged along by the spin. But you haven't crossed the point of no return yet. You can still escape. And in 1969, Roger Penrose, the same Penrose who proved the singularity theorem, realized that this region allows for something remarkable. You could, in principle, extract energy from a spinning black hole. The idea is called the Penrose process, and it works like this. You send an object into the ergosphere, and inside the ergosphere, you split it into two pieces. One piece falls into the black hole on a trajectory that actually reduces the black hole's spin. It enters with what physicists call negative energy relative to an observer at infinity, which sounds impossible, but is allowed by the weird geometry inside the ergosphere. The other piece gets flung back out with more energy than the original object had going in. You've extracted rotational energy from the black hole itself. The black hole slows down slightly, and you've gained energy. It's like, imagine a spinning flywheel, and you could somehow bounce balls off it in just the right way that the balls come back faster than you threw them, while the flywheel gradually slows down. You're mining the rotational energy, and the numbers are not trivial. Theoretically, you could extract up to about 29% of a spinning black hole's total mass energy through this process. 29% of the mass of a black hole converted to usable energy. That's an astonishing amount. For a stellar mass black hole, that's more energy than our sun will produce in its entire lifetime, available in principle just by cleverly exploiting the geometry of the ergosphere. Now, nobody's actually going to build a Penrose process engine anytime soon. You'd need to be operating right next to a black hole, splitting objects apart with incredible precision inside the ergosphere. But the principle matters because it tells us something deep about what a black hole actually is. A spinning black hole isn't just a passive drain, it's a reservoir of energy. It has extractable energy stored in its rotation, and the laws of physics allow that energy to be tapped. And this connects to something even more profound that came along a few years later, in the early 1970s, when a set of ideas emerged that would completely transform how physicists thought about black holes. It started with a young physicist named Jacob Bekenstein, who was a graduate student of John Wheeler's at Princeton. Bekenstein asked a question that seemed almost naive at first, but turned out to be revolutionary. Does a black hole have entropy? Now, entropy is one of those concepts from thermodynamics. It's a measure of disorder, or more precisely, a measure of how many microscopic arrangements could produce the same macroscopic state. A cup of hot coffee has high entropy because the molecules could be arranged in countless ways and still look like a cup of hot coffee. A perfectly ordered crystal has low entropy because there's essentially only one way to arrange the atoms. The second law of thermodynamics says that entropy in a closed system always increases. Things get more disordered over time, never less. It's one of the most fundamental laws in all of physics. But here's the problem Bekenstein noticed. If you throw something into a black hole, say a box full of hot gas with lots of entropy, that entropy seems to just vanish from the universe. The gas is gone, behind the event horizon, and the black hole just sits there, looking the same as before, described by its mass, charge, and spin. nothing else. So where did the entropy go? If the entropy truly disappeared, then you've just violated the second law of thermodynamics. You've decreased the total entropy of the universe by dumping it into a black hole. And that bothered Bekenstein enormously, because the second law isn't just some minor rule. It's one of the pillars that all of physics rests on. Bekenstein's radical proposal, published in 1972 and 1973, was that the black hole itself must carry entropy, and that this entropy is proportional to the area of the event horizon, not the volume, the area, the surface area of the event horizon. Every time you throw something into a black hole, the mass increases, the event horizon grows, and the entropy of the black hole increases by at least as much as the entropy of whatever you threw in. The second law is saved, but now it's a generalized second law. The total entropy of everything outside the black hole, plus the entropy of the black hole itself, never decreases. This was a strange and beautiful idea, and initially, a lot of physicists thought Bekenstein was wrong. His own advisor, Wheeler, was supportive, but many others were skeptical. Because if a black hole has entropy, then by the laws of thermodynamics, it should also have a temperature. And if it has a temperature, it should radiate energy, like any warm object does. But black holes are black, nothing escapes from them. So, how could they radiate? The whole idea seemed to lead to a contradiction. And that's exactly where Stephen Hawking entered the picture, initially intending to prove Bekenstein wrong, and instead discovering something that would change our understanding of the universe forever. Hawking in the early 1970s was already one of the sharpest minds in theoretical physics, and he'd been doing extraordinary work on black hole mechanics. He'd actually just proven, in 1971, a beautiful theorem showing that the total area of all event horizons can never decrease. If two black holes merge, the area of the new horizon is always at least as large as the sum of the two original areas. Think about that for a second. That sounds an awful lot like entropy, right? Entropy never decreases. Horizon area never decreases. Bekenstein had noticed exactly this parallel and built his entire proposal on it. But Hawking himself was annoyed by Bekenstein's interpretation. He felt Bekenstein was taking a mathematical analogy too literally. Yes, the equations of black hole mechanics looked like the equations of thermodynamics. Horizon area played the role of entropy. Surface gravity played the role of temperature. But Hawking thought this was just a formal resemblance, not deep physics. Because if you took it seriously, you'd have to accept that a black hole has a real temperature, and a real temperature means real radiation, and real radiation means something is escaping the black hole, which is absurd. Nothing escapes a black hole. That's the whole point. So Hawking set out to demolish Bekenstein's idea by doing a proper quantum mechanical calculation near the event horizon. He wanted to show rigorously that black holes don't radiate, that the thermodynamic analogy was just a coincidence, and that Bekenstein had overreached. He spent months on this calculation in late 1973 and into 1974, applying quantum field theory to the curved space-time around a black hole. And what he found shocked him. It shocked everyone. Black holes do radiate. Here's how it works, and I want to walk through this carefully because it's one of the most beautiful results in all of physics, and it's also one of the most misunderstood. You've probably heard the popular explanation that pairs of virtual particles pop into existence near the event horizon. One falls in, one escapes, and that's Hawking radiation. That story is everywhere, and it's not exactly wrong, but it's a cartoon version. Let me give you something a little closer to what's actually going on. Start with quantum field theory, which tells us that empty space isn't really empty. Even in a perfect vacuum, fields are fluctuating. There's a kind of irreducible quantum fuzz everywhere. Now, in flat, boring space-time, no gravity, no curvature, all observers agree on what empty means. They agree on what a vacuum is. They agree that there are zero particles present. But here's the thing that makes everything strange. In curved space-time, different observers can disagree about how many particles exist. This isn't a philosophical point. It's a mathematical result. The definition of particle depends on your reference frame. And when space-time is curved, especially when it's curved dramatically like near a black hole, different observers can have fundamentally different but equally valid descriptions of the same physics. What Hawking showed is that an observer far from the black hole, someone floating safely at a great distance, would detect a faint but steady stream of particles coming from the direction of the black hole. To that distant observer, the black hole is glowing, very, very faintly, but genuinely glowing. The spectrum of that radiation, the pattern of wavelengths, turns out to be exactly thermal. It's a perfect blackbody spectrum, the same kind of radiation you get from a hot oven or a warm coal. And the temperature of that radiation depends on the mass of the black hole in a beautifully simple way. The temperature is inversely proportional to the mass. Smaller black holes are hotter. Larger black holes are colder. And when I say cold, I mean astonishingly cold. A black hole with the mass of our sun would have a Hawking temperature of about 60 billionths of a Kelvin. 60 nanokelvin. That's not just cold. That's colder than the cosmic microwave background radiation that fills all of space, which sits at about 2.7 Kelvin. So a solar mass black hole is actually absorbing more energy from the cosmic background than it's emitting through Hawking radiation. It's gaining weight, not losing it. For any black hole formed from a collapsed star, Hawking radiation is so feeble that it's completely undetectable, completely irrelevant to the black hole's behavior on any timescale that matters to the current universe. But here's where it gets interesting. Think about what happens if you had a very small black hole. As the mass decreases, the temperature goes up. And as the temperature goes up, the black hole radiates more intensely. And as it radiates more, it loses mass faster. And as it loses mass, it gets even hotter. You see where this is going? It's a runaway process. A black hole that's losing mass through Hawking radiation accelerates its own evaporation. The smaller it gets, the faster it shrinks, the hotter it burns, until in the very final moments, the last tiny remnant of the black hole should explode in an extraordinary burst of energy. The final second of a black hole's life would release something like the energy of 1,000,000 megaton nuclear bombs. It goes out with a bang, not a whimper. Now, for a stellar mass black hole, this process would take an almost incomprehensible amount of time. We're talking something like 10 to the power of 67 years. That number is so large it's meaningless in human terms. The current age of the universe is only about 1.4 times 10 to the 10 years. So we're talking about time scales that dwarf the age of the universe by a factor of 10 to the 57. But the point is that it's finite. Black holes are not eternal. Given enough time, every black hole will evaporate completely and disappear. And that was a revolution. Before Hawking, black holes were forever. They were the ultimate endpoints of gravitational collapse. Matter goes in, nothing comes out, end of story, for all eternity. After Hawking, black holes became temporary objects, incredibly long-lived but temporary. They're born, they exist, and eventually they die. Hawking published this result in 1974 in a paper in the journal Nature, and then a more detailed version in 1975. The reaction in the physics community was a mixture of awe and deep unease. Because Hawking hadn't just confirmed Bekenstein's intuition, he'd gone further. He'd derived the exact formula for the entropy of a black hole. The Bekenstein-Hawking entropy, as it came to be known, equals 1/4 of the event horizon area measured in Planck units. And the numbers are staggering. A black hole with the mass of the Sun would have an entropy of roughly 10 to the 77. For comparison, all the ordinary matter in the observable universe, every star, every planet, every cloud of gas, has a total entropy of maybe 10 to the 88. A single, supermassive black hole at the center of a galaxy can carry more entropy than trillions of stars. Black holes are the most entropic objects in the universe. They are, in a very real sense, the ultimate repositories of disorder. And this is where the story takes its most unsettling turn, the one that physicists are still arguing about today. It's called the black hole information paradox, and it's arguably the deepest problem in theoretical physics. Let me set it up for you. In quantum mechanics, there's a principle called unitarity. It basically means that information is never truly lost. If you know the complete quantum state of a system at one time, you can in principle reconstruct its state at any other time, past or future. Quantum mechanics is deterministic in this deep sense. The information about what went into a process is always encoded in what comes out. It might be scrambled beyond any practical hope of recovery, but it's there. Think of it like burning a book. In classical terms, the book is destroyed. The information is gone. But if you could somehow track every single particle of smoke, every photon of light, every ash fragment, every molecule of gas, and you had unlimited computational power, quantum mechanics says you could reconstruct the entire text of the book. The information isn't destroyed by burning, it's just dispersed. Now apply that to a black hole. You throw a book into a black hole. The black hole's mass increases, its horizon grows, and it settles down into a slightly larger black hole, described only by mass, spin, and charge. All the specific information about the book, what was written in it, what it was made of, every quantum detail, seems to have vanished behind the event horizon. But that's okay, you might say, because the information is still there. It's just inside the black hole. We can't access it, but it exists. But then Hawking radiation happens. The black hole slowly evaporates. And here's the crucial point. Hawking showed that the radiation is exactly thermal. It's random. It carries no information about what fell into the black hole. It's like the static on a detuned radio. Pure noise, with a characteristic temperature but no message. A black hole that formed from a collapsed library would emit exactly the same Hawking radiation as a black hole of the same mass that formed from collapsed iron. The radiation doesn't know what went in. So if the black hole evaporates completely, and the radiation carries no information, then the information about everything that ever fell into the black hole is simply gone, erased from the universe. And that violates unitarity. That breaks quantum mechanics. Hawking himself, for decades, argued that information really is lost, that black holes destroy information, and quantum mechanics needs to be modified to account for this. This was a bold and deeply controversial position. Most other physicists, and I mean most, believed that information must somehow be preserved, that there had to be a mechanism, maybe one we don't yet understand, by which the information sneaks out in the Hawking radiation in some incredibly subtle, scrambled form. This became one of the great intellectual battles of late 20th century physics. On one side, Hawking, arguing that gravity is special, that it really does destroy information, that the rules change at event horizons. On the other side, people like John Preskill at Caltech and Leonard Susskind at Stanford, arguing that unitarity is sacred, that quantum mechanics doesn't break, that the information has to come out somehow. In 1997, Hawking and Kip Thorne made a famous bet with Preskill. Hawking and Thorne bet that information is lost. Preskill bet that it's preserved. The wager was an encyclopedia of the winner's choice, Preskill's idea, a charming touch. And in 2004, at a conference in Dublin, Hawking conceded. He said he'd been wrong, that information is preserved, and he gave Preskill a baseball encyclopedia. Thorne, notably, did not concede, and many physicists felt that Hawking's concession was premature, that we still don't have a complete, satisfying answer to how the information gets out. The paradox, in many ways, remains open. But here's why this matters beyond just an abstract puzzle. The information paradox sits at the exact intersection of quantum mechanics and general relativity, the two greatest theories in physics, both spectacularly successful in their own domains and yet fundamentally incompatible with each other. General relativity describes gravity as the curvature of spacetime. Quantum mechanics describes everything else, particles, forces, fields, in terms of probabilities and wave functions. Each theory works brilliantly on its own. But when you try to combine them, when you try to write down a quantum theory of gravity, you get nonsense, infinities, contradictions, and the black hole information paradox is the sharpest, clearest manifestation of that conflict. It's the place where the two theories stare at each other across a divide and flatly contradict one another. Which is exactly why so many of the brightest minds in physics have spent the last 50 years working on it. And one of the most remarkable developments in that quest came from a direction almost nobody expected, from a theoretical idea about the relationship between gravity and quantum information that would come to be known as holography. Not holography in the sense of those shimmering stickers on your credit card, though the name does come from the same Greek root, holos, meaning whole. This is something far stranger. It's the idea that all the information contained within a volume of space can be perfectly encoded on the boundary of that space. That the three-dimensional world you experience might, in a very precise mathematical sense, be a projection of information living on a two-dimensional surface. And if that sounds like science fiction, well, it did to a lot of physicists too, at first. But it emerged from very serious work, and it has become one of the most important ideas in theoretical physics in the last 30 years. The seed was planted by Gerard 't Hooft, the Dutch Nobel laureate, in 1993. He was thinking about exactly the problem we've been circling. What happens to information at a black hole horizon? And he noticed something peculiar about the Bekenstein-Hawking entropy formula. Remember that formula? The entropy of a black hole, the amount of information it contains, is proportional to the area of its event horizon, not the volume enclosed by the horizon. The area. Think about why that's strange. If you have a room full of gas molecules, the entropy of that gas, the number of possible arrangements of all those molecules, depends on the volume of the room. Double the room, roughly double the entropy. That's how things normally work in physics. Information content scales with volume. But for a black hole, the information content scales with surface area. And since the black hole is the densest possible object you can have, You literally cannot pack more information into a given region of space than a black hole does. This means there's a fundamental limit on how much information any region of space can contain. And that limit is set not by the volume, but by the area of the boundary surrounding it. 't Hooft took this seriously. He suggested that this isn't just a quirk of black holes. He proposed that it might be telling us something deep about the nature of reality itself, that the true degrees of freedom of any physical system, the fundamental bits of information that describe everything happening inside a region, actually live on the boundary of that region. The interior is, in some sense, a reconstruction, a projection, like a hologram. Now, this was a radical idea, and it might have remained a provocative speculation if not for what happened 2 years later. In 1997, the same year Hawking and Thorne made their bet with Preskill, actually, a young Argentine-American physicist named Juan Maldacena, working at Harvard, published a paper that would become the most cited paper in the history of high-energy physics. And I mean that literally. As of recent counts, it has been cited over 20,000 times. That's extraordinary for any academic paper, let alone one in theoretical physics. What Maldacena did was construct a concrete, mathematically precise example of the holographic principle in action. He showed that a specific theory of gravity, a version of string theory, living in a particular curved spacetime called anti-de Sitter space, is exactly equivalent to a quantum field theory living on the boundary of that spacetime. Not approximately equivalent, not kind of similar, exactly equivalent. Every calculation you can do in the gravitational theory has a precise counterpart in the boundary theory, and vice versa. Two completely different-looking theories, describing what seem like completely different physics, are secretly the same theory written in different languages. This is called the ADS/CFT correspondence. And let me unpack that name just a little because it helps you understand what's going on. A DS stands for anti-de Sitter space, which is a particular geometry of spacetime. It's negatively curved, like the inside of a saddle, and it has a boundary at infinity. CFT stands for conformal field theory, which is a particular type of quantum field theory. No gravity, just particles and fields, living on the boundary of the anti-de Sitter space. The correspondence says these two descriptions are dual to each other. They're two windows into the same room. Here's what's really clever about this, and why it matters so much for the information paradox. In the boundary theory, the quantum field theory, there's no gravity at all. It's just ordinary quantum mechanics, and ordinary quantum mechanics is unitary. Information is always preserved. Always. It's baked into the mathematics. So if the gravitational theory in the interior is truly equivalent to this boundary theory, then the gravitational theory must also preserve information. Even when black holes form and evaporate, the information has to come out. Maldacena's duality doesn't tell you exactly how the information escapes. It doesn't give you the detailed mechanism, but it gives you a proof of principle. It says, look, in this mathematical universe, black holes form, they evaporate, and information is preserved because the whole process has an equivalent description in a theory where information preservation is guaranteed. That's a big deal. That's a really big deal. It shifted the center of gravity of the debate. Before Maldacena, you could still reasonably argue, as Hawking did, that maybe information really is destroyed. After Maldacena, the weight of evidence tilted strongly toward preservation. This is part of why Hawking conceded to Preskill in 2004. The ADS/CFT evidence was becoming overwhelming. But let's pause here for a moment, because I want you to appreciate something about the texture of how physics actually works. Maldacena didn't solve the information paradox. He didn't explain the mechanism by which information gets out of a black hole. What he did was provide a framework, a stage on which the question could be asked more precisely. And that framework turned out to be incredibly fertile. It spawned entire subfields. It connected string theory to condensed matter physics, to quantum information theory, to nuclear physics. People used ADS/CFT to model the quark-gluon plasma produced at particle accelerators, to study superconductors, to explore quantum entanglement. It became a universal tool, a Rosetta Stone between gravitational physics and quantum physics. And one of the most beautiful developments to come out of this framework, something that would have been almost unimaginable when Bekenstein first proposed black hole entropy in 1972, is the deep connection between gravity and quantum entanglement. This is where the story gets genuinely mind-bending, so settle in. Quantum entanglement, as you probably know at least vaguely, is the phenomenon where two particles can be correlated in a way that has no classical explanation. You measure one, and you instantly know something about the other, no matter how far apart they are. Einstein famously called it spooky action at a distance, and thought it showed quantum mechanics must be incomplete. But entanglement is real. It's been confirmed in countless experiments, and it turns out to be far more fundamental than even its discoverers realized. In 2006, a physicist named Shinsei Ryu and his collaborator Tadashi Takayanagi, working in the context of ADS/CFT, proposed a remarkable formula. They showed that the amount of entanglement between two regions of the boundary theory, the quantum field theory, is related to the area of a particular surface in the bulk gravitational theory. Specifically, the entanglement entropy between region A and the rest of the boundary equals the area of the minimal surface in the bulk that is anchored to the boundary of region A, divided by 4 times Newton's gravitational constant. If that formula reminds you of the Bekenstein-Hawking entropy formula, area divided by 4g, it should. It's the same structure, and that's not a coincidence. What the Ryu-Takayanagi formula is telling you is something profound. It's saying that the geometry of space-time, the shape of the gravitational universe, the curves and distances and surfaces, is built from entanglement. Entanglement isn't just some weird quantum correlation that happens within space-time. Entanglement is what makes space-time. The fabric of space itself is woven from quantum entanglement between microscopic degrees of freedom. Think about that for a second. The distance between 2 points in space, the thing you measure with a ruler, the most basic geometric concept there is. That distance might emerge from the pattern of quantum correlations between underlying degrees of freedom. When things are highly entangled, they're close together in the emergent geometry. When entanglement is disrupted, space itself can tear apart. Mark van Ramsdonk, a physicist at the University of British Columbia, put it beautifully in a 2010 paper. If you gradually reduce the entanglement between 2 halves of a quantum system, the corresponding space-time geometry develops a longer and longer bridge between them, until eventually, when the entanglement reaches 0, the space-time pinches off into 2 disconnected pieces. Entanglement is the glue that holds space together. And this brings us back to black holes in a way that's almost poetic. Remember the event horizon? That boundary in space-time beyond which nothing can escape? In this entanglement picture, the horizon is a surface where the entanglement structure of space-time is organized in a very particular way. The Bekenstein-Hawking entropy, that quarter area formula that started this whole journey, is now understood as a measure of entanglement. The entropy of a black hole is the entanglement entropy between the interior and the exterior. And when a black hole evaporates via Hawking radiation, what's really happening in this picture is that the entanglement is being gradually transferred from entanglement between the interior and exterior to entanglement between the early and late Hawking radiation. This insight led to one of the most important recent developments in the information paradox saga, something called the Page curve. Don Page, a Canadian physicist who was actually one of Hawking's former students, proposed back in 1993 that if information is preserved during black hole evaporation, then the entanglement entropy of the radiation should follow a specific pattern. Early in the evaporation, as the black hole emits radiation, the entanglement entropy of the radiation should increase. The radiation is becoming more and more entangled with the shrinking black hole. But at some point, roughly the halfway point of the evaporation, called the Page time, the entropy should start decreasing because the radiation is now beginning to purify itself, to contain enough information to start reconstructing what fell in. By the time the black hole has completely evaporated, the entropy of the radiation should be back to zero. All the information has come out, and the radiation is in a pure quantum state. For decades, nobody could derive the Page curve from a gravitational calculation. Hawking's original calculation just showed the entropy going up and up and up forever, which is exactly the information loss scenario. But in 2019, a series of breakthrough papers by Jeff Pennington and independently by Ahmed Almhairi, Netta Engelhardt, Donald Marolf, and Henry Maxfield showed that by carefully including certain quantum gravitational effects, specifically new saddle points in the gravitational path integral called quantum extremal surfaces, and contributions from space-time geometries called replica wormholes, you could derive the Page curve directly from the gravitational theory. The entropy goes up, reaches a maximum at the Page time, and then comes back down. Information is preserved. This was a genuine watershed moment. For the first time, the gravitational calculation itself, not just the boundary dual, not just an argument by analogy, was telling you that information comes out. The gravitational theory, when you do the calculation carefully enough, is consistent with unitarity. Hawking's original calculation wasn't wrong, exactly. It was incomplete. It was missing contributions that only become important at very late times, after the Page time, when the black hole has radiated away more than half its initial entropy. Now, I want to be honest with you, because this is the kind of thing where it's easy to overstate the conclusion. These results are spectacular, but they come with caveats. They work cleanly in the context of ADS/CFT, in anti-de Sitter space, which is not the spacetime we actually live in. Our universe appears to have a positive cosmological constant. It's closer to de Sitter space, which has very different properties. Extending these results to realistic cosmologies is an open and active problem. And even within ADS/CFT, we still don't have a completely detailed, microscopic account of how information gets out. We know it does. We can show the entropy follows the right curve, but the blow-by-blow mechanism, the precise way in which the information is encoded in the Hawking radiation, remains elusive. But the direction of travel is clear, and it's pointing toward something remarkable. It's pointing toward a picture of reality where space-time itself is not fundamental, where the geometry you and I experience, the three dimensions of space we move through, the distances between objects, the curvature that we call gravity, all of it emerges from a deeper layer of quantum information, entanglement, quantum error correction, computational complexity. The language of quantum information science is turning out to be the language you need to describe the deep structure of space-time. And black holes, those extreme objects that once seemed like the universe's most exotic curiosities, are the key that unlocked this understanding. Which brings us to something I haven't talked about yet. Something that takes all of this beautiful theory and grounds it in cold, hard observational reality. Because while the theorists were arguing about information and entanglement and holography, the observers and experimentalists were doing something extraordinary too. They were building a telescope the size of the Earth, and they were about to take a picture of a black hole. Not an artist's impression, not a simulation, not a diagram in a textbook. An actual image captured from real photons that had traveled across intergalactic space. Photons that had grazed the edge of one of the most violent objects in the known universe and somehow made it all the way to dishes and receivers scattered across our little planet. The project was called the Event Horizon Telescope, and the story of how it came together is one of those engineering sagas that sounds impossible until you realize they actually pulled it off. The basic problem is simple to state. Black holes are small, absurdly, comically small for how massive they are. The supermassive black hole at the center of our own Milky Way, Sagittarius A star, has a mass of about 4 million suns. That's enormous. But its event horizon, the part you'd actually want to image, is only about 24 million kilometers across, which sounds big until you remember it's 26,000 light-years away. From Earth, that shadow subtends an angle of roughly 50 micro-arcseconds. To give you a sense of what that means, it's like trying to read the date on a coin in Los Angeles while you're standing in New York, or spotting a grapefruit on the surface of the moon. Your eye can't do it. No single telescope on Earth can do it. The resolution of a telescope, its ability to distinguish fine details, depends on the ratio of the wavelength of light you're observing to the diameter of your dish. If you want to resolve something 50 micro-arcseconds across using radio waves at a wavelength of about 1.3 millimeters, which is the wavelength you need because it can punch through the hot gas and dust swirling around the black hole, you'd need a dish roughly the diameter of the Earth, about 13,000 kilometers across. Nobody's building a dish that big. But here's the thing. You don't actually need a single dish. You need a technique called Very Long Baseline Interferometry, VLBI. The idea goes back decades. If you have two radio telescopes separated by a large distance, and they both observe the same source at the same time, and you very precisely record the exact arrival time of the radio waves at each dish, you can later combine those recordings and extract information about the source's structure at a resolution corresponding not to the size of either individual dish, but to the distance between them. The baseline. So if your two dishes are on opposite sides of the Earth, your effective resolution is that of an Earth-sized telescope. You don't get the same sensitivity, you're still only collecting photons with your actual dish areas, but you get the sharpness, the angular resolution, of something planet-sized. VLBI had been used in radio astronomy since the late 1960s, but doing it at 1.3 millimeters at 230 gigahertz was a completely different beast. At those short wavelengths, the Earth's atmosphere becomes a serious problem. Water vapor absorbs and distorts the signal. You need your telescopes at high, dry sites, mountaintops, deserts, polar plateaus, where there's as little atmosphere above you as possible. And you need atomic clocks at every site, hydrogen maser frequency standards, to timestamp your data with a precision of better than a trillionth of a second. And you need to record data at staggering rates, many gigabits per second, onto banks of hard drives that then get physically shipped to a central location for correlation. In the early days of the EHT project, they were literally FedExing crates of hard drives because no internet connection on Earth was fast enough. The effort was led by Shepard Doleman at what was then the MIT Haystack Observatory, and it grew over years from a proof of concept with just a few stations into a global collaboration involving over 300 researchers and 8 telescope sites on 6 continents, including the South Pole Telescope in Antarctica, the ALMA Array in Chile's Atacama Desert at 5,000 meters elevation, telescopes in Hawaii, Arizona, Spain, Mexico, and France. Each of these facilities had to be outfitted with compatible receivers, identical recording systems, and those hydrogen maser clocks. The coordination was immense. You needed clear weather simultaneously at all sites. You needed the Earth's rotation to sweep out enough baseline coverage, because as the Earth turns, the effective baseline between any 2 telescopes changes, filling in more of what's called the UV plane, which is essentially the coverage map of spatial frequencies you're sampling. More coverage means a better image. The first global observing campaign that had enough stations to attempt a real image happened in April 2017. Over the course of several nights, all 8 stations pointed at 2 targets, Sagittarius A star at the center of our galaxy, and M87 star, the supermassive black hole at the heart of the giant elliptical galaxy Messier 87, about 55 million light-years away. M87 star is far more distant than Sgr A star, but it's also about 1,500 times more massive, 6.5 billion solar masses, so its shadow appears roughly the same angular size on the sky. And crucially, because it's so much more massive, the timescale on which the swirling gas around it changes is much longer. Hours instead of minutes. That made it a steadier target, easier to image. Then came 2 years of processing. The data, about 5 petabytes of it, half a ton of hard drives, was shipped to correlator centers at MIT Haystack and the Max Planck Institute for Radio Astronomy in Bonn. The correlation process is painstaking. You're looking for the faint interference pattern between signals recorded at stations thousands of kilometers apart, signals that passed through different patches of turbulent atmosphere, signals that need to be aligned to sub-wavelength precision. The teams developed multiple independent imaging pipelines, different algorithms, to make sure the result wasn't an artifact of any one method. They ran blind tests. They generated synthetic data from simulations, scrambled it, and checked whether their pipelines could recover the known input. They were meticulous because they knew what was at stake. On April 10, 2019, the image was released simultaneously at 6 press conferences around the world. And there it was, an asymmetric ring of light, bright orange and yellow in the false color rendering, surrounding a dark central shadow. The ring was the emission from superheated plasma spiraling around the black hole at relativistic speeds, plasma heated to billions of degrees, glowing in synchrotron radiation. The dark center was the shadow, the region where photons had been captured by the black hole's gravity and could never reach us. The asymmetry, the fact that one side of the ring was brighter than the other, was exactly what general relativity predicted. The material on the side moving toward us gets relativistically boosted, Doppler brightened, while the material on the receding side dims. The size of the shadow matched the prediction for a 6.5 billion solar mass black hole within the uncertainties. General relativity, tested now not in the weak field regime of Mercury's orbit or GPS satellites, but right at the edge of an event horizon, passed with flying colors. Think about what that image represents. Einstein published his field equations in 1915. Schwarzschild found his solution in 1916. For decades, most physicists thought black holes were mathematical curiosities that nature would never actually produce. And then, 103 years later, we photographed one. We took light that left a galaxy 55 million years ago. Light that was emitted when our ancestors were small, lemur-like creatures. And we caught it with dishes on mountaintops and combined it with algorithms running on clusters of computers. And we reconstructed an image of the very thing that Einstein's equations predicted. But Einstein himself never believed was real. 2 years later, in 2021, the EHT collaboration released a polarized light image of M87 star. Polarization tells you about the magnetic field structure in the emitting region. The image showed a distinctive spiral pattern in the polarization vectors, which constrained models of how magnetic fields thread through the accretion disk and help launch the relativistic jet. That enormous beam of plasma that M87 shoots out for thousands of light years. In May 2022, they released the first image of Sagittarius A star, our own galactic center black hole. This one was harder. The gas dynamics change on timescales of minutes, so the source was effectively flickering during the observation. The team had to develop new methods to handle that variability, essentially averaging over thousands of possible snapshot images to find the common underlying structure. Again, a ring. Again, the right size. Again, general relativity confirmed. And the EHT isn't done. Next-generation upgrades are already underway. Adding more stations, dishes in Africa, Greenland, new sites in the Pacific, will fill in the UV plane coverage and sharpen the image dramatically. Moving to shorter wavelengths, to 0.87 millimeters, will improve resolution further. The goal is to eventually make movies. Actual time-resolved sequences showing the hot gas orbiting and plunging into the black hole in real time. Imagine watching matter spiral in, seeing the bright spot orbit around, watching the dynamics of space-time curvature playing out frame by frame. That's not science fiction. That's a funded engineering project with a timeline. But the EHT wasn't the only observational revolution. Just a few years before that first image, a completely different kind of telescope, if you can even call it a telescope, heard something that had never been heard before. On September 14th, 2015, at 5:51 in the morning Eastern Time, the twin detectors of LIGO, one in Hanford, Washington, and one in Livingston, Louisiana, simultaneously registered a signal, a chirp, a rising frequency, a crescendo, and then silence. The whole thing lasted less than a second, but packed into that fraction of a second was the story of two black holes, each about 30 times the mass of the Sun, that had been spiraling toward each other for millions of years, moving faster and faster, closer and closer, until in the final moments they were whipping around each other at nearly the speed of light. And then they merged. They became one. And the energy released in that merger radiated away as gravitational waves, as ripples in the fabric of space-time itself, was enormous. For a brief instant, that collision radiated more energy than all the stars in the observable universe combined. And LIGO caught it. Now, the engineering behind LIGO is its own kind of marvel, and it's worth pausing to appreciate just how absurd the measurement challenge was. Gravitational waves stretch and squeeze space as they pass through, but the amount of stretching is incredibly, almost incomprehensibly small. We're talking about a change in the length of LIGO's 4-kilometer-long arms by about 1/10,000th the diameter of a proton. Let that sit for a moment. A proton is already so small you can't see it with any microscope ever built, and LIGO needed to detect a change in distance that's a fraction of that. It's like measuring the distance from Earth to the nearest star and being able to tell if that distance changed by the width of a human hair. That's the kind of precision we're talking about. And the way they achieved it is beautiful in its simplicity, at least conceptually. LIGO is essentially a giant laser interferometer. You split a laser beam in two, send each half down one of two perpendicular arms, each arm 4 kilometers long, bounce them off mirrors at the far ends, and bring them back together. When the two beams recombine, they interfere with each other. If the arms are exactly the same length, the light waves cancel out in a very specific way. But if a gravitational wave passes through and stretches one arm while squeezing the other, even by that absurdly tiny amount, the interference pattern shifts, and you can detect that shift. Now, the concept is simple. The execution is anything but. Think about all the things that could mimic that signal. A truck driving by on a nearby highway, a tiny earthquake on the other side of the world, thermal vibrations in the mirror, ocean waves crashing on a distant shore. And yes, ocean waves really do create seismic noise that LIGO has to filter out. The mirrors themselves are suspended on quadruple pendulum systems, each stage isolating against vibrations at different frequencies. The laser beam bounces back and forth inside the arms about 300 times before recombining, effectively making the arms act as if they're about 1,200 kilometers long instead of 4. The vacuum inside the beam tubes is one of the largest sustained vacuums on Earth, about 1/trillionth of atmospheric pressure, because even stray air molecules bouncing off the laser beam would ruin the measurement. And here's a detail I love. The two detectors are separated by about 3,000 kilometers, and they're both needed precisely because of all that noise. Any real gravitational wave signal should appear in both detectors, separated by a tiny time delay, no more than about 10 milliseconds, the time it takes light to travel between the two sites. If something shows up in only one detector, it's probably local noise. If it shows up in both, with the right time delay, you might have something real. That's exactly what happened on September 14th, 2015. The signal appeared in Livingston about 7 milliseconds before it appeared in Hanford. And when the team ran the analysis, the waveform matched general relativity's prediction for a binary black hole merger with stunning precision. The event was designated GW 150914 for the date, and the paper announcing it, published in February 2016, had over 1,000 authors. Kip Thorne, Rainer Weiss, and Barry Barish shared the Nobel Prize in Physics in 2017 for it. Weiss had originally proposed the basic LIGO concept back in 1972. Thorne had been pushing for it from the theoretical side for decades, and Barish was the project director who, in the mid-1990s, essentially saved LIGO from being canceled by reorganizing the entire management structure and getting it funded and built. It took over 4 decades from concept to detection. 40 years of people believing they could measure something that small, convincing funding agencies, building the thing, rebuilding it, upgrading it, and waiting. And what they heard, that chirp, told them so much. The frequency of the gravitational waves corresponds to twice the orbital frequency of the two objects spiraling together. As the black holes get closer, they orbit faster, so the frequency rises. That's the chirp. It sweeps upward. The rate at which the frequency changes tells you the masses of the two objects. The amplitude tells you how far away the merger happened. In this case, about 1.3 billion light-years. And the shape of the waveform, the precise way the amplitude and frequency evolve, tests general relativity in the strong field regime, where gravity is most intense, where space-time is most violently curved, in a way that had never been possible before. And general relativity passed. Every prediction matched. Since that first detection, LIGO and its European partner Virgo have detected dozens more gravitational wave events, binary black hole mergers of various masses. And in August 2017, something different, a binary neutron star merger, designated GW170817. That one was special, because neutron star mergers produce not just gravitational waves, but also light, electromagnetic radiation across the spectrum. Telescopes around the world swung to the source and saw a kilonova, the radioactive glow of heavy elements being forged in the aftermath. Gold, platinum, uranium, created right there in the collision of two dead stars. That single event connected gravitational wave astronomy to traditional astronomy in a way that opened an entirely new era of what people now call multi-messenger astrophysics. You're not just looking at the universe anymore. You're listening to it and matching what you hear with what you see. But let's come back to the black holes themselves, because all of these observations, the EHT images, the LIGO detections, they confirm something extraordinary. Black holes are real. They're not mathematical curiosities. They're not artifacts of an idealized equation. They exist. They merge. They swallow light. They warp space-time so severely that they create shadows you can photograph and vibrations you can measure with laser beams in Louisiana. And yet, for all that we've confirmed, there's so much we still don't understand. The information paradox, the one Hawking and Susskind and everyone else argued about for decades, it's still not fully resolved. The replica wormhole calculations and the quantum extremal surface work showed that the page curve comes out right in certain theoretical setups, which strongly suggests that information is preserved, that black hole evaporation is unitary. But those calculations were done in anti-de Sitter space, which has a boundary, a nice mathematical container. Our universe doesn't look like that. Our universe appears to have a positive cosmological constant. It's expanding, accelerating, de Sitter space, not anti-de Sitter. And nobody has a clean version of the holographic principle for de Sitter space. Not yet. That's one of the biggest open problems in theoretical physics right now. How do you formulate quantum gravity in a universe that looks like ours? And then there's the singularity. General relativity predicts it. An infinitely dense point at the center of every black hole where the curvature of space-time blows up, where the equations break, where physics as we know it simply stops making sense. Most physicists believe the singularity isn't real, that it's a signal that general relativity is incomplete, that some theory of quantum gravity, whatever it turns out to be, will resolve the singularity into something finite, something comprehensible. Maybe it's a Planck density core. Maybe space-time itself has a discrete structure at that scale, like pixels in a photograph, and you simply can't squeeze matter into a space smaller than one pixel. Maybe the singularity bounces, and the interior of a black hole connects to a baby universe, a new region of space-time budding off from ours. These are real proposals that serious physicists work on. None of them are confirmed. The interior of a black hole is, almost by definition, the hardest place in the universe to get information from. And that's what makes this field so alive right now. We're in this remarkable moment where observation and theory are finally converging on black holes from multiple directions. The EHT is getting sharper. LIGO is getting more sensitive. The next generation of detectors, like the Einstein telescope planned for Europe and Cosmic Explorer proposed for the United States, will be able to detect black hole mergers all the way back to the earliest epochs of the universe, when the first stars were forming and collapsing. The James Webb Space Telescope is finding supermassive black holes at surprisingly high redshifts, black holes that seem too massive too early, which challenges our models of how they grew. Did they start from the collapse of enormous primordial gas clouds? Did they grow by merging with each other? Did some exotic process in the early universe seed them? We don't know yet. And on the theoretical side, the tools developed to study the information paradox, entanglement entropy, holographic duality, quantum error correction applied to space-time. These are reshaping our understanding of what space-time itself is. There's a growing sense among many theorists that space-time is not fundamental, that it emerges from something deeper, something quantum mechanical, something to do with entanglement and information. The black hole, in this view, isn't just an object in space-time. It's a window into the nature of space-time. It's the place where the usual rules break down hard enough that you're forced to confront what lies beneath. Think about how far we've come. John Michell, in 1783, sitting in his rectory in Yorkshire, imagining a star so massive that light couldn't escape. He had no real theory of gravity beyond Newton, no concept of space-time, no quantum mechanics. He was just following a thought to its logical conclusion. And now, 2.5 centuries later, we've photographed the shadow of a 6.5 billion solar mass black hole in a galaxy 55 million light-years away. We've listened to the space-time vibrations of 2 black holes merging over 1 billion light-years from Earth. We've built a theoretical framework that connects the entropy of a black hole to the quantum information of a holographic boundary, and we're using that framework to ask whether space and time themselves are woven from entanglement. Every step of that journey involved someone being willing to take an idea seriously that sounded absurd. Schwarzschild solving Einstein's equations in the trenches of World War I and finding a solution with a point of no return. Chandrasekhar, barely 20 years old, realizing on a steamship that massive stars had no choice but to collapse. Oppenheimer and Snyder, in 1939, showing that an observer watching from outside would see the collapse freeze at the horizon while the infalling matter experiences something entirely different, a smooth passage through, into whatever lies beyond. Wheeler, who resisted the idea for years, finally giving it the name that stuck. Penrose, proving that singularities weren't artifacts of symmetry, but inevitable consequences of general relativity. Bekenstein, a graduate student, having the audacity to suggest that black holes have entropy. Hawking, initially furious at the idea, then discovering radiation that made it all consistent, and in doing so, accidentally uncovering the deepest puzzle in physics. Susskind, refusing to let information die. Maldacena, connecting 2 seemingly unrelated theories and giving everyone a new playground. And the experimentalists, Doleman and the EHT team, Weiss and Thorne and Barish and the LIGO collaboration, building instruments of almost impossible precision and patience. All of those people, across centuries, across continents, were working on the same question, really. What happens when gravity gets so strong that it overwhelms everything else? And the answer keeps getting richer. Every time someone thinks they've reached the bottom, there's another layer. The singularity isn't an ending, it's a question mark. The horizon isn't a wall. It's a one-way door that encodes information on its surface. The black hole isn't a destroyer. It might be the universe's most efficient information storage device. And you know what's quietly wonderful about all of this? Right now, tonight, as you're lying here, there are black holes everywhere. Stellar mass black holes scattered through our galaxy, the remnants of massive stars that burned out millions or billions of years ago. Sagittarius A star, sitting at the center of the Milky Way, 4 million solar masses, relatively quiet right now, just occasionally snacking on a wisp of gas. Supermassive black holes at the centers of nearly every galaxy you could point a telescope at. And out in the voids between galaxies, gravitational waves are rippling past us right now, stretching and squeezing space by amounts so small that only the most extraordinary instruments ever built can feel them. The universe is humming with the echoes of black hole mergers that happened billions of years ago, and that hum is passing through you, through the room you're in, through the earth itself, at this very moment. There's something peaceful about that, I think. The universe is doing all of this. Collapsing stars, bending light, radiating entropy, preserving information in ways we're only beginning to understand. And it's doing it quietly, constantly, everywhere. You don't have to do anything about it. You don't have to solve the information paradox tonight. You can just know that it's out there, that the questions are beautiful, that the people working on them are brilliant and stubborn and human, that the story isn't over, not even close, and that somewhere right now, someone is staring at an equation or a data set or an image, and they're about to notice something that nobody has noticed before, and it will change what we think we know, and the story will get a little richer, a little deeper, a little more astonishing. But that's for tomorrow. For now, this is enough. The stars are doing what they've always done. The black holes are patient, and you can rest.